So let me also, in the second hour, we may start talking about ray tracing. So what I'm going to do is I'm going to, I believe also you did not put the ray tracing geometry slides on Opticlass. So for the second hour, if you want to take notes, I'm just going to quickly add a file for today's lecture. So that add a file for ray tracing. Let me call it ray tracing geometry so that you can download it during the break if you want to take notes on it. Alright, so there's no description. Let me just put the file that I have here, ray tracing geometry PDF. Actually, I wasn't planning to use any slides. I was just going to talk about ray tracing geometry on the board, but we may need to refer to these slides, so that's why I did that. Alright, so now on Opticlass we have ray tracing geometry slides that we may start talking about in the second hour today. Alright, yeah, good morning again everyone. So let's start today's lecture. Where we left was we were talking about images and cameras, and we are going to continue on human visual system. So the important things that we are going to cover today are the integer values that we give to intensity values, to the pixels. So every pixel, if you remember, our images from last time are nothing but an image is a rectangular 2D matrix and 2D array of pixels like this. Which are square most of the time. Sometimes they may be rectangular depending on how you're viewing them. There may be different displays around the world in which the pixels are hexagonal. Okay, so there is no, I mean, this is not a physical fact. All right, so, and therefore, this is just a general convention people use for images these days. A person asked me like a couple of years back. He asked me what the size of a pixel is. So we're talking about pixels, 1 megapixel, 2 megapixel. So I got a call from outside actually to my office, and this person was wondering what is the size of a pixel. And the answer is it really depends. I mean, if you're looking at a very large LED screen or a billboard, on a billboard you may have like a screen that is of 10 meters by 20 meters wide, 10 meters wide, 20 meters long, and in that case your pixels may be as large as a couple of centimeters each. But on your phone, you also have a very large, display, high-resolution display. But that high-resolution display is confined to a very small area. In that case, the sizes of the pixels are going to be small. Okay, so the size of pixel it really depends on the hardware. The resolution, when we talk about the resolution, when we say 1 megapixel, or it's for example 1920 by 180 or things like that. So we have these different resolutions that we can have. For example, when I create a new image here on GIMP, where is GIMP? So when I say new, it asks me what the image size is. If you look at this, width and height, so this is like a landscape image with longer width than height. We may also have different orientations. We may have a portrait orientation in which the width is smaller than the height. Okay, so it really depends. But if you look at this one, it's basically a 2 megapixel image. Will have this many. There are roughly 2 million pixels. There will be this many pixels if you are going to use an image of resolution. So 2 megapixels is actually quite large, as you can see, 2000 by 1000, which gives you 2 million pixels. But we have cameras that can actually take pictures of even larger than 20 megapixel, so 10 times larger than this. Since the area increases the square of the size of the individual lengths, so if, for example, you roughly increase each dimension by 3 times. For example, if this becomes a 6000 by 2000 image, it will roughly be so 3 times 3 is going to be 9, so it's going to be 9 times larger than this original one, so it's going to be like a 20 megapixel image. All right, so this the megapixel information just gives us, it doesn't give us anything about the sizes where you're going to be printing or where you're going to be displaying it on an actual screen. So in that case, the hardware pixel sizes will also come into picture. But yeah, we're not going to talk about these. When we're generating images, we will just talk about a rectangular area like this with a specified height and width. But when we have these images, when in ray tracing, for example, this image is going to be generating in a three-dimensional. So while we are running the algorithm, we will place this image window, the image itself, on a three-dimensional virtual world as if it's in front of our eyes. This is where the photons, the light rays, are going to be collected upon. So it's going to, we are going to mimic very much actual cameras, where the camera, each camera, for example, has a sensor array behind a lens. That sensor array collects light rays, photons, and then turns them into electrical signals that can be written on your disk. So this is very similar to what happens in our retina as well. The one interesting fact is that since the lenses are in front of the, so I'm talking about an image plane like this, right? But what actually happens is that that image plane is behind the lens. So as the light rays pass through the lens, the image actually is formed upside down. So let me just quickly write it here. Okay, so when the light rays come here, so if there's a lens here, and if the image plane, so this is actually your retina, when it passes through this, so they're focused on, so the image actually, well, while it passes through those, for example, a tree that is here, its top is going to appear at this pixel, at this point in your image plane or retina, and the bottom of the tree, if this is a tree that a pine tree, for example, the bottom of the tree is going to appear here in this pixel, which means that if you look at this image plane in upright position, the tree is going to appear as if it's projected upside down. So what we're going to do is, in our ray tracing algorithm, since we are free to replace these virtual entities in our imaging system. By the way, this happens in perspective vision. In perspective vision, light rays come through, pass through a lens, and then projected upon some sensor array like this. This may be your retina and your rods and cones in your retina, these cells, it may be those, or it may be the sensor array behind a camera. Okay, behind the camera lens. So what we're going to do is we're going to take this one and place it, take this part and place it in front of the camera. Okay, the image plane is going to be like in front of the lens, which is not what we have in real life naturally, but it will be, we are going to assume light rays come through these points and they merge at some focal point while they're coming. So this way, when the light rays merge into a focal point of some lens, okay, what will happen is that we are going to have perspective vision. I'm going to talk about this in more detail, but one effect of moving the image window, the image plane, from behind the lens to in front of the lens is that the images that we generate, so we are going to have a tree that is projected upon this image, as you can see again, in upright position. So this point here is going to fall into this place. So one thing you can say at this point is that, why are we just looking at this ray? Aren't there many rays coming from all over the place that also pass through this pixel? If that happens, actually, you get if there are multiple images that contribute to a single pixel on an image, what is the effect of this? you get blurry images. Okay, when something is like out of focus, if multiple objects contribute to the same pixel, you get blurry images. In order to avoid that, the very early cameras from maybe in 19th century, for example, very early cameras, there was this pinhole camera model. The pinhole camera model is something like this. There is a box, okay? This box has a very small pinhole. So you just, actually you can build such a camera today in your home. So this is like a homemade camera. All you need is a light-sensitive material that this may be like a film that you're going to develop later. So whatever light-sensitive material you have here, you can place it at the back of this box. And what you're going to do is you're going to open a very tiny pinhole. The reason that you have this very tiny pinhole is that you don't want many, for example, look at this, let me use a different color. Look at this point, for example, on the sensor. If and there's an object here, there's another maybe object here. If these objects, if the light ray, if this hole is really small, only a light ray coming from a specific direction is going to pass through this hole and hit this one. If you have a larger hole here, multiple light rays can also pass through this large hole and hit the same spot, which will make this spot on the film to have contribution from many different objects maybe. This is how it will occur blurry. It will not be sharp. In order to have a sharp image, you have a very small hole here that makes it a pinhole camera, and in that case what happens is that only a specific light ray comes here. This light gets contribution only from this point on this object, which will help us create a very sharp image. But what is the disadvantage of having a very small pinhole? One disadvantage was back in 19th century early cameras was that you had to wait a lot of time for this picture, for enough number of light rays to be collected on this film. Since this hole is very small, only small amount of light can enter from this pinhole. Therefore, when you just take a picture, for example, in 1 second, you will get a very dark image. Very small amount of photons will be able to enter and hit this particular spot. Therefore, when people were taking pictures in early 19th century, maybe they had to wait like 10 minutes, 15 minutes. So it's like say cheese, and they were like saying cheese for 10 minutes. And maybe that's why if you look at very early photographs, these people look very stressed, and not stressed, but I mean they're not like you can see that they have been standing for 10 minutes to have their picture taken. So we are going to use a similar model in ray tracing. When we talk about ray tracing geometry, we will actually be we will be modeling a pinhole camera like this, but the only difference will be, again, in this pinhole camera, the image is going to be formed upside down on this image. What we are going to have is, we are going to have this film in front of this, which doesn't happen in real life. I mean, if you have it in front of the pinhole, what is the purpose of pinhole? I mean, all the light rays are hitting this. You cannot have such a real camera. But since we are doing this in a virtual world, we can have our model formed with this modification, and we will talk about this soon today. All right, but let's come back to our images and display topic, which was these pixels. When the photon, the intensity we have here on this pixel, we indicate it as an 3-byte integer. If it's a color image, what we have is 1 byte per color channel. We have values from 0 to 255 that change linearly. Now, today what we are going to see, I started my sentence as we are going to see two important things today, but I didn't mention them yet. One of them is this linear change in color values from 0 to 255. What was Control-Shift-J? Yeah. So the color values from 0 to 255, for example, if this is green, the integers increase like this, right? I mean, they're linearly, we have different levels from 0 to 255, 256 different color levels. Now, what would you expect? For example, if you give a value of 128 or 127 to a pixel, you would expect it to be half red, okay? Or if this was just a grayscale value, if this is, for example, black, and if this is like white, you would want 128 to be exactly a middle gray in between black and white, okay? Now, the problem with hardware, and also there's a problem with human cognition, is that our brightness perception, how we perceive brightness, and another thing is in hardware, how the voltage levels. So you're going to give these integer values to your display, monitor, hardware, saying that make this pixel this bright. So if you follow this linear thing, the thing with voltage levels is that when you apply half the voltage to the same pixel, it doesn't actually get half bright. The problem is that the voltage levels and the corresponding illumination, luminosity on the pixel, they are not linear. So one thing we are going to see is that this, which is called this gamma correction. This non-linear relationship between voltage and the actual luminosity, intensity, there's a non-linear relationship, but our pixel values are linear like this. In order to make this voltage also, behavior also linear, something is applied on these numbers before they are converted into voltage values, and that's one is called gamma correction. So each monitor has some gamma that you can play with. So there's a value gamma which makes this non-linear relationship between voltage and intensity to try to turn to linear one. There is another non-linear relationship, not, as I said, not in hardware, but in human hardware, in our perception, human cognition. We don't perceive a linear change in luminosity as linear with our eyes. Okay, so that's another thing. So these are the two things that we are going to be talking about in the first hour. I mean, in the remaining half an hour, I will talk about this gamma correction, and I will talk about human cognition, also how we perceive brightness differently. There are other aspects in cognition too, like when you're looking at highly textured material, for example, there's an object with detailed textures on it. Its color actually affects how you perceive the detail. For example, it's known that blue acuity, this is called acuity, the ability to perceive details. Okay, so for example, blue acuity is lower than red acuity. So if you want to have show some detailed textures, detailed small text, for example, that is on an object, for example, presenting it blue will decrease the way it's perceived. The details will be difficult to be perceived. So, oh yeah, so also when you say 128, so we have slides on this. Do we perceive it a little bit closer to the white or closer to the black when we exactly have some gray in the middle? We have a slide actually on this in human cognition, and I'm going to perform that experiment with you. So I'm not going to answer your question right away, but we are going to talk about that. Yeah, I'm going to ask this question to you actually when I present you the images. I will ask you the same thing. The middle one, is it closer to white or is it close to black? We'll see that. But anyway, so this is about perception, how we perceive things, and how the hardware also treats these integer linear levels as nonlinear. Okay, so actually I summarize everything I'm going to talk about, so we are going to go over the slides and talk about these details. So we talked about image formats, how we can compress images in JPEG, lossy compression, and in PNG we have lossless compression. And in this class, we're going to be generating these simple PPM format images with our programs. So when we, OpenGL actually directly renders to the screen. In order to, if you want to write a C program that renders to your monitor, you can actually use different libraries in C to do that. And OpenGL provides us, and actually it's not OpenGL that provides us this context, but there are libraries like GLUT, and we are going to be using another library, for example, the glue library with OpenGL, in order to have actually it's not glue. I forget the name of the library that we replaced with GLUT. GLUT is a very old library, but it's still you can use. But what I'm trying to say is that if you want to render something onto the screen, you need some. You cannot do it in pure C. There is one thing called SDL, I think, not STL, but which can manage multimedia in different platforms in C programs. And which in that case you can get a graphics context from your monitor, and you can actually, instead of writing this PPM to a file, you can, whatever you generate as image, you can directly render it on screen. Computer graphics applications, they do that actually. If you have a computer graphics application, you want to see your output immediately on the screen. And we are going to see, I think there's SFML, and there's, I remember it was like something SDL. Let me, OpenGL, SDL. I think it was SDL. Yeah, it's this one. So SDL library, when you search for SDL library. So it's direct media player. But the thing is, I think it's, is it available? libstl.org. So this direct media layer, you can actually, there are some applications that uses this. So if you want to, so even there are some games that use SDL. It's a cross-platform development library designed to provide low-level access. It's not only for getting graphics context, but also audio, keyboard, mouse, joystick, graphics, hardware via OpenGL and Direct3D. So you can use both of them. And what we are using is actually a different library. So OpenGL compile. Actually, I have it here. OpenGL compile. If I look at OpenGL setup, so I'm going to take a look at these. So I'm quickly looking at. So we are going to be using glue, but I think it's GLFW. Yeah, it's the GLFW library is the one we are going to use. GLFW. When we come to OpenGL, we will be using this GLFW library in addition with OpenGL, because OpenGL does not provide the necessary functions to open up a window and render on that. So we need two libraries. If you are when we are going to write our computer graphics applications in OpenGL, we are going to be using the OpenGL library, but OpenGL just treats, all the OpenGL functions are in the 3D virtual world. It doesn't deal with the hardware itself. And therefore, we are going to be using this GLFW library, which is currently maintained. It's modern, so many applications use this. It's even Vulkan is supported now, which is the new. Oh, so there was a Mac actually did something really radical and just completely dropped OpenGL from its development. The Mac, so they have their own Mac applications now have to use this Vulkan library if they want to have graphics applications. But GLFW supports both. So if you look at what it is. It provides a simple API for creating windows, contexts, and surfaces receiving input and events. So how you're going to have an interactive application by using your keyboard. OpenGL does not have any functions about that. So if you want to have a keyboard mouse interaction, you want to open up a window, make it full screen, things like that, you need another library, and this is what we are going to be learning in the second half of the course. Now in the first half, we are going to be generating our images and writing them to files like this. You don't want to give this burden to you to learn SDL2 and the first part of the course. So what the programs you will be writing are going to be very simple. We are going to take a picture of a virtual world and we are going to write that picture information. So we are going to compute these pixel values. Our ray tracing algorithm is going to compute the pixel value in a, if you're going to, for example, generate a 2 megapixel image, this 1920 by 180 resolution, we are going to find the pixel color values of 2 million pixels. So our main loop in a ray tracing application will be for every pixel. So that main loop is going to run 2 million times. And for each pixel, we are going to ask this question: what color is this pixel? Okay, is it red? Is it gray? Is it purple? So the entire ray tracing algorithm, its purpose is going to be to find the color of a pixel, what color it should be. Okay, so how are we going to do that? It's a really nice algorithm. It has some geometry involved in it. We are going to generate a ray. The first step will be, so okay, this is the pixel. This pixel, which light ray passes through this pixel? Now, our first job is to find the equation of that light ray. And this light ray is going to be a ray in the virtual three-dimensional world. How do we represent rays? How do we represent line equations in 3 dimensions? So this week we are going to have a recitation. I think it's tomorrow, right? Kadir Cenkalpay, your teaching assistant, is going to have a recitation on this linear algebra and some background mathematics, which is going to cover some of this material I'm going to also talk about in ray tracing geometry. But it's really simple. For lines, for example, we will be using parametric line equations, which is really simple to handle in 3 dimensions. And after we generate our ray, okay, we know the light ray that passes through this pixel. And this next question is, what color is the light that passed through this ray? What is the color we see at that point? So at that point, you're just going to imagine yourself with a very tiny telescope looking over that light ray, along the light ray, and you're going to ask yourself, what do I see here? So you have to see your light ray is going to, you're going to see something. If in this pixel there's a very small pinhole camera at this exact center of this pixel, what that pinhole camera at that point receives is what we will ask. And you may actually have some ideas about how we're going to proceed, right? For example, if there are many objects in your scene, which object will you be seeing? The frontmost object, for example, this light ray, we are going to perform ray object intersection test. We are going to intersect this light ray with our objects in the 3D world. We are going to ask question whether this light ray, does it intersect this sphere? Does it intersect this cube? If it intersects, we are of all the intersecting objects, we will be concerning ourselves with the one that is closest to us. out of all the intersections, because the light ray just, it's going to, the light ray equation is going to penetrate all the objects. It doesn't, we don't have the information when we are doing the intersection test. We don't have an information about which object is in front, we don't store the relationship objects with each other. Actually, we could do that to speed up intersection tests, but in the original algorithm with no optimizations whatsoever, we are going to treat each object separately and ask whether this ray intersect with my object. And we are going to keep track of where the intersection point is. And after we finish intersection of this light ray with all the objects in our scene, and our primitive objects in the scene will be like triangles or spheres most of the time, or some polygons, or if you have the mathematical definition of a sphere, it may be, you may also use spheres. We will see these two objects actually in our scenes. We will just have, our scenes will be composed of thousands of triangles and maybe a couple of spheres. And you're going to intersect your light ray with thousands of triangles each time, and keep the closest intersection. And whatever the color of that triangle is, this is what you're going to be seeing in this pixel. But is just color of the object enough? For example, the object may be red color. Are we going to see a red color here like this? What if the object is not facing the light directly? What if it's so there will be, maybe we are going to see, you may have a red sphere in 3 dimensions. Are you seeing all part of the red sphere with the same red in a scene, in a real life scene? No, certain parts are, so there's something called shading. It's not shadow. Shadows and shadow is something different. Shadow is something, a part of an object in which the certain light rays don't ever reach. Okay, don't get ever reflect. That's what a shadow is. The light rays don't reach that surface, and you don't actually get the reflected light from that particular light source. That's what a shadow is. But shading is something different. Shading is the process that light ray that is reflecting off a surface is reflected at different amount depending on how that surface is facing the light source. If it's if it can be bouncing directly from the surface, you get more light. If it's if the surface is a little bit, for example, if I have a light ray that is coming directly to the surface like this, it bounces off most of the light photons. But if it is a little bit inclined like this, if my surface is like this and this is still the light rays are coming, some of them are going to not bounce, and the ones that are bouncing towards you are going to be less. So taking into account this less light bouncing of the surface, this is what we are going to do. I mean, I just summarized actually what we will be doing in the ray tracing algorithm, but we will write an algorithm that takes these steps, that makes these computations step by step. At the end, compute a value for this pixel, and it will do it 2 million times for every pixel. Very inefficient, right? I mean, so when we're going to draw a single sphere, we're not going to have a sphere drawing code, for example. We're just going to have a ray sphere intersection code, which will say, okay, this is a part of a sphere, it's red. This is not a part of sphere, it's the background, that's why it's gray. So, and the sphere appear on this image as like a circular projection, not because we draw a circle here, because of our ray sphere intersections are going to determine these are the pixels. These are the light rays through these pixels that intersect with your sphere. So by treating each pixel separately, at the end we will take pictures of these virtual worlds, and it will be really rewarding to see your first sphere correctly on the screen. Actually, if in the second hour, maybe we can even do that real time. I may try to write the code for that if we finish the geometry. Okay, so but let me continue with the gamma correction now. So we talked about images, JPEG. Video is just a sequence of images and it's compressed differently. Now, we talk high dimensional, high dynamic range imaging. I'm skipping that part as well. We talked about this earlier. The thing is that in real life, the quantization levels are not just, the luminosity levels are not just 256 different levels. The difference between your lowest luminance, lowest intensity, and highest intensity, their ratio may be a lot larger than 256. So you may need a different mapping of your actual scene range. So this is what high dynamic range imaging is about. Now, there are different display devices. Some of them are portrait, some of them are landscape. They have different sizes. Look at these different size monitors. In all of them, I may have a 10 megapixel image, which means that the pixel sizes will be different in these different devices. Now, here is the part where we get to our gamma correction stuff in the last 6 slides or so. The digital signals that we have, those color levels, they are actually before you see the light field of your monitor, they are converted to some analog voltages in the display device. And these voltages determine the luminance emitted from each pixel, and the voltage to luminance relationship is nonlinear. So as you increase your output luminance, so as we increase this here, let me annotate. So this is image pixel value. I think it's also like correspond to the voltage value. If we just give the image pixel value as voltages directly, the luminance actually increases faster. If it was non-linear, if it was linear, it will be like this, or maybe I didn't. I mean, this isn't linear. When I say linear, it doesn't need to be one-to-one. Okay, for example, every increase in every 2 pixel value may be increase in 1 in luminance value. But this is still, when you have a line like this, it may either be, it may be like this. This is also linear. This is also linear. Okay, so you may have linear correction about these things easily. So, but what we see, the curve we see here is it gets steeper. I mean, if we had something like this, a curve like this, it would mean that when you increase the value, the luminance increases in a nonlinear manner, but slowly. So we can have, for example, a square root or log function like this. But this one is like maybe a nonlinear relationship in which the observed brightness increases faster. So we need to make this appear linear, and this is what is done to the voltages. So what you do is, this is your voltage. You raise the voltage value to some gamma value, and to make it decrease, to have the output luminance appear linear. So this gamma value has to be something small, right? Less than 1, so that you just suppress the voltage values to be nonlinear. So this is the brightness value you have from your pixels that you can get. So what you do is, so actually this is the ideal is a gamma value of 2.2. So I think it's the nonlinear relationship is, there's also some constant factor that is involved here. So gamma correction is actually the input signal is the input signal is not raised to the power of gamma. So yeah, it becomes something, a value less than 0, as you can see. This one is saying that the voltage is raised to the power gamma, but as you can see in this when the gamma value is 2.2, the input signal is raised to the power of 1 over lambda. That was the actual voltage value. So whatever the signal we have here, the pixel value, we raise it to the power of 1 over gamma before being stored in that voltage. Okay, so all you need to do about this gamma correction is that it's used to have to match the linearity of luminance in hardware devices. So here are different examples. So when you play with the gamma of your monitor, if you don't have the gamma correction, it will appear like this. Maybe certain parts are going to be darker. When we do the gamma correction, the contrast between different colors, dark and light colors, will be more linearly spaced. Okay, so this like histogram correction, make it a more uniform distribution between color levels. And also in computer graphics, gamma correction can be applied to the pixel integer values too. When you compute, for example, pixel values, applying gamma correction may make your image less dark. So this one is gamma corrected. I think this one is not gamma corrected at the pixel level. Okay, so if you need to learn more about gamma correction, you can take a look at this web page that Oğuz shared. So, as I said, I don't want to go into too much the detail of this gamma correction. All you need to know is that it's changing the nonlinear relationship between voltage values in hardware to linear in pixel value, in what we have in pixel values. Now, the second thing before we go into break is the human visual system. And here again, there are different aspects about perception and how we, after the gamma correction, the light levels tend to be linear, but it's still not, doesn't match our real life cognition. For example, here's a gamma corrected image. Let me come to this one. So imagine these values are gamma corrected, okay, and actually our monitor has gamma correction. So right now there is a fixed amount of luminosity decrease between these levels, okay. So we can have, after we apply gamma correction, we have equal change in luminance, the light rays bouncing off these rectangles. It's linearly, the pixel values may be linearly increasing, therefore the luminance differences between these two also, these three images also linearly increases. But do we perceive it like that? Yeah, that's coming to your question. It's not actually, we don't perceive it like that. Now let me ask you this question, the middle one. If think about this middle one, it's equidistant in luminance to the left one or to the right one. But how do you perceive it? Is it closer to the light gray one or the dark gray one? And I mean, if you, yeah, let me ask you this question. What do you perceive? Yeah, closer to the right. I think so too. I mean, this one, I mean, these two are more alike. I mean, if you just give me every two of them as pairs of rectangles and match the ones that are closer to each other, I will try to cluster these two together because I would think this one is closer to this gray. Okay, so in perception there is these nonlinear things all over the place. For example, there was another thing about nonlinearity I noticed when I was proctoring exams. It was the crowdedness of an amphitheater, crowdedness of a classroom. For example, for example, half the students leave the classroom, but the crowdedness perception I have is, I mean, I just count the papers, for example, as the students leave the exam. So it actually, maybe 25% of the students leave the classroom, but I feel like it's as if half has already left. Okay, so it gets empty much quicker than the actual relationship. So if the same thing happens in perception all over different aspects of life. So yeah, this is the non-linearity in luminous difference in human cognition as well. So do we need to? So why do we need to take this into account, the human cognition? Do we really want to perceive everything linearly as our pixel values? Maybe change your gamma values to match these things. It may be in some cases. Some games have some adjustment before. If you just download a game and run it the first time. Some games actually have your monitor set up before you start playing the game to have the best experience. For example, it says, for example, adjust your brightness such that you see this on the left, but you don't see it on the right, or adjust your contrast such that you don't see the boundaries between these rectangles. It looks smooth. Things like that. You must have come with such kind of adjustments when you're playing the games first time. That's all about this cognition probably. They do the setup. You can play with the gamma values or other brightness contrast values so that what you perceive is something close to what our goal is. So there is no universal. It also shows that if these games make you do these adjustments differently, there is no universal truth about this. I mean, the perception may change from person to person too. Okay, we are not all equally alike. For example, we know that there's color blindness, which is much more common than we think actually, and there are different levels of color blindness. Color blindness just doesn't mean that you cannot distinguish between any green or any red. So if you are provided a shade of orange looking thing that is also somehow greenish, maybe some people are worse at distinguish this orange and green as different shade of green and orange. They may have difficulty in distinguish those. So there are different levels of color blindness. It's not something binary, okay? And the same thing with color cognition as well. The may change between human to human. So here's some biology about human visual system. We have the actual cognition happens in the brain. So the retina, the picture is upside down, and our brain actually compensates about lots of things. We use some visual clues like shadows to understand whether something is above a surface or on the surface. So there are lots of visual clues around us, and our brain makes use of these visual clues a lot to interpret the environment. And there's optical illusions. They actually make use of this brain's compensation. Sometimes the brain overcompensates certain things. And some magicians, for example, use this to their advantage. For example, we focus on certain parts, or we see things differently in different lighting environment, lighting conditions. For example, you see this paper as a white paper, right? It's like a white paper, but the luminance I received in this room, probably I compare it with its surroundings. If somehow I have a way to capture this luminance on this white paper, and if I had to see it out in an outside environment with lots of sunlight, probably that paper is going to appear as gray. That luminance would appear as gray outside. Okay, so and you may have also seen these different optical illusions, these images that circulate around the web that says, okay, that like a checkerboard. You must have seen that checkerboard in which there's a cup on the checkerboard, and the cup casts a shadow on one part of the checkerboard. But since and there's black, white, but the white in the shadow is actually the black you see. They have exactly the same intensity, luminance, as the black that is not in shadow. So it's really hard you sometimes find yourself covering the other parts of the image to really verify that they have the exact same gray values. So brain compensates about lots of things. So I already told you that. So there's the lens. Here's a tree, a much better tree than I tried to draw. And the light rays pass through our lens, and there is a certain part. This is our retina. There are color sensitive and light sensitive cells here, so photosensitive cells. and a certain part of our optic nerve actually has to cover part of our retina. That's where our blind spot is. So certain light rays coming to here we cannot see. So there's an image actually to check your blind spot. I'm going to come to that quickly. But there are different types of photosensitive cells, rods and cones. Some of them are, the rods are better, I think. It was the rods that are better at perceiving low light vision. So they have different levels of sensitivity. And we have certain types of cell that are concentrated on our peripheral. So this is like through evolution, we have developed different parts. For example, you can catch movement at your peripheral much faster, and at your peripheral you are more sensitive to photons. It's like not color vision, gray vision, but you can you can see in low light conditions. For example, you may also try this experiment in a very dark room. For example, just in a dark room, but not too dark. Still, there's some amount of light in the room. Imagine like a dark room, but a very small light passing through some window or something. You may have this experiment where you may place an object directly in front of you, have the room dark enough so that you don't see the object that is you place in front of you. Okay, but you may see that when you move the object to your periphery, even in the same, you don't do anything about the change in lighting condition, the object, you may be able to see it when it's in your peripheral vision. Okay, so which shows that certain cells that are in our periphery are it's also, I have, thank you, Yusuf, for this comment. I didn't use it before, so I didn't, I have noticed this in a dark room with objects, but to see the stars in a dark, the sky in a dark environment also, seeing stars with your peripheral vision is probably better than looking at directly to them. Yeah, that's a very good suggestion. So if you close one eye, and you can actually, if you look at this slide, yeah, also in city light, there is light pollution. It's difficult to see stars anyway. But if you close one eye and look at this, focus on the crosshair, the plus sign, you'll see that at certain distance, if you look at, get your head close to the monitor, the dot on the left disappears. You really don't see it. It's as if there's only one thing on the slide. Okay, so it's where the light rays coming from that blind spot, actually, that circle on the left is actually falling on our blind spot. Therefore, there are no signals generated for that. Okay, so our retina has a blind spot. So rods are only active under low light conditions, and cones are good for, there are three types of cones, just like the red, green, blue channel. So this three-color channel modeling, three-channel color modeling is actually coming from biology. There are three different types of cones sensitive to different types of wavelength of light. For example, so if you look at, they're not just partitioned in the wavelength space. So blue cone, for example, with the blue cones, they're more sensitive to blue wavelength light. But there's, as you can see, there are some overlaps between red and green. Oh, and you can see why there's color blindness, right? I mean, the green cone and red cone in our retina, they overlap a lot actually. So it may be difficult to distinguish between red and green wavelength, especially in colors in this region. So, and there's also nonlinearity I mentioned. So here is, this is about that, so I'm going to skip. We also talked about this. So if you make the pixel value difference equal in your scenes, don't expect the person is going to perceive equal luminance differences between those grades. So, so we can actually have some kind of a gamma correction of our cells when you're having our computer graphics applications. So this is that non-linearity thing. So you can take a look at this example later. So if you want to if you want to show equal luminance in between these two things, you can see that after we apply the correction, the perceived brightness, we can say, for example, there is more difference if you put more. This is the perceived difference we have actually in the pixel values. Okay, so this is where I want to stop. Just some general information about human cognition, perception. These are just general information. We didn't talk about any algorithm at all. I think it will be a lot more fun if we talk about, we start talking about the actual method and start right ahead, right away, and start implementing our first ray tracing solution. So it's really interesting to be able to take a picture of a virtual world. Okay, so that's it for these sets of slides. Let's have a 10-minute break now until 10:45. So it's actually a 9-minute, close to 9-minute break. I'm going to stop recording the first part.